Good day, everyone. So today we're going to talk about Chapter 14, Inferential Techniques for Regression. Um, and so we're not going to go over all the things that are in Chapter 14. There's a lot there. Uh, we're not meant to go. We're not meant to go over the whole thing. Let's face it. There's a lot there, and so the authors just put in there just about everything that an intro course could possibly go over, and then they'd rather put in too much than not enough is essentially it, and then the professor decides what he or she wants to go over and eliminate the rest and not talk about the rest. Now, if you have forgotten about regression in Intro 1, or if you took a class that didn't require you to take Intro 1 because you already took a stats course and you have forgotten about regression, I have put up my video from Intro 1 um, in this right next to this uh, video, and you can take a look at it first. Okay, but if you do recall regression and you want to keep on going, great. So remember, with regression analysis, we're looking at the relationship between essentially quantitative variables. Okay, so here was the example that I gave back in Intro 1, where we had latitude as x, and, and then we had average January temperature for y. And remember, x is the explanatory, y is the response variable, and there's the different cities, and so we want to see if there's some sort of significant relationship between x and y, latitude and average January temperature. All right, and then we went ahead and created a scatter plot. So there was our scatter plot, and so you can see our sample regression line in red. You can also call that the least squares regression line. Those are interchangeable. All right. And if you did this in StatCrunch, you would go to Stat, Regression, Simple Linear. Notice we put in latitude for X, average January temperature for Y, and then I just hit compute. Okay, and this was the output that I got. And what I want to concentrate on a little bit more, I did already a little bit in Intro 1. I'll mention a couple of things up here again that we see, and then we'll add a little bit to it that we didn't talk about. So I just copied everything over. All right. And eventually we're going to get to this stuff down here, but I want to kind of concentrate at the top right now. So there's our sample regression line. Okay, that's the least squares regression line. And remember, this is in the form of y is equal to the y-intercept minus the slope times x. So the slope is negative. That means we have a negative relationship between average January temperature and latitude. So as latitude goes up, meaning you are heading further north, what's going to happen to average January temperature is going to get colder. All right. So I want you to think about this. Now, notice in this slide right here, I went ahead and highlighted and put in red. It's the sample regression line. Okay. And let's think about this for a second. When I did this originally, I just sort of randomly thought of cities. And I want you to think about what would happen if I didn't bring in Lincoln, Nebraska. So Lincoln, Nebraska was in the original data. But instead of bringing in Lincoln, I brought in LA instead. So here's our data. So Lincoln's gone, and I replaced it with LA. What would have happened? Now, this would have been a perfectly acceptable random sample of 10 cities. Okay, it's just that instead of bringing in Lincoln, I brought in LA. Think about what would happen then. So what's going to happen is that the slope and the y-intercept will change slightly, right? For example, this was what we got with the original analysis for the sample regression line. And this is with LA. So notice things changed a little bit, okay? The y-intercept certainly changed. It changed a little bit, right? Changed by 12 units. And then the slope just changed just a little bit, right? Just a little bit. but certainly would change. All right. And so what did we just learn? We just learned that the y-intercept and the slope from the sample regression line are statistics, and they vary from, you guessed it, sample to sample, just like every other statistic. And since this is the case, each should have its own sampling distribution. All right. So each should have its own sampling distribution. So we are going to talk about more about that later on. All right. Okay, then we had our sample size of 10, and we have our correlation coefficient of a negative 0.9826. So that's a strong correlation coefficient, right? That's indicating a very strong negative relationship between these two variables. We had an R squared of 96.54%. That's a high R squared. We talked about R squared in depth in Intro 1. What we didn't talk about is this number right here, what StatCrunch is referring to as the estimate of error standard deviation. Honestly, this is given a lot of different names. The way I like to think of it is the estimate. So why is it an estimate, first of all? Because we don't have the entire population, okay? We only looked at a sample, so it's an estimate of something, all right? So it's an estimate of what? Standard deviation. What does standard deviation do? It measures variation. So it's an estimate of variation somehow of all the values of y at any given x. All right. It's great just to kind of say it, but what exactly does that mean? All right. What exactly does that mean? So what to understand this, what I want you to think about is this, is that we're just going to look at one value of x, and we'll say 41. And there's actually, I know it only looks like 2 cities, but there's actually 3 cities here because 2 cities are sitting exactly the same spot. Cleveland and Lincoln, Nebraska are sitting exactly the same spot. And then you have New York up here, all right? So Cleveland and Lincoln's down here, and here's New York. So all 3 sit at 41 degrees latitude. So think about this. In our sample, we had just 3 cities, right? But certainly there's more cities in the United States that are at 41 degrees latitude, right? And so pretend that we could look at all the different cities sitting at 41 degrees latitude, not just Cleveland, New York, and Lincoln, all right, but all of them, all right? And let's pretend to make a dot plot of all these cities, all right? So here, notice what's down here. It says here, all U.S. cities average January temperature at 41 degrees latitude. So we're at 41 degrees latitude, okay? But these are all the different U.S. cities. And there's Cleveland, there's Lincoln, Nebraska, and then there's New York City, okay? Well, let's say then, well, let's continue down this path. It says, what does this have to do with S then? Well, S is the standard deviation of all the y values at each value of x. So this suggests that there's a distribution at each value of x. So in other words, there's a distribution at 41 degrees latitude, there's one at 40, there's one at 42, 43, 29, so on and so forth. At each value of x, the standard deviation should be roughly the same. That's what we're saying here, and that's what we're estimating with S. Okay, so I know this goes over the axis, bear with me. So we should be able to do this at another latitude. For instance, at 39 degrees latitude, maybe the average January temperature for those cities is not 25 like it is here. So notice the average January temperature is 25, but it's 30. However, the standard deviation should be roughly the same as it was at 41 degrees latitude. So let's pretend to go ahead and make a dot plot of all the cities, not at 41 degrees latitude, but say 39. So here's all the cities at 39 degrees latitude. Notice it's at 30, the center. However, what's still roughly the same as before? The standard deviation of all these values. Okay, so this graph right here, should be roughly the same. Now I made it exactly the same, but they should be roughly the same. That's standard deviation. And so that's what S is estimating, is that it's the standard deviation at 39 degrees latitude. It's the standard deviation of the y's at 41 degrees latitude. It's the standard deviation of the y's at 10 degrees latitude. All right. No, probably not 10. That might be too low. Maybe 25 degrees latitude. Okay. So that's what S is. And to calculate S, all it is that if you go down to this table right here and go down to, we'll just call this MSE for right now, the mean square error. If you take the square root of this number right here, okay, you get S. All right, and we'll talk about this lower table here in a little bit. All right, if we compared multiple models, we would rather have an S that is smaller. And that's important. Often we want to compare multiple models, and we shouldn't just look at one thing. We should look at multiple things. And so one of the things that we should look at is, well, you know, we'd rather have a smaller variation, okay, than a larger one. Simple as that, okay? And so we would want this to be smaller if we're comparing two separate models. All right, what about this this upper table here? Let's talk about this. So first of all, each of these lines is its own hypothesis test. All right, so this line right here and this line right here are both separate separate hypothesis tests. Okay, but what are they testing? No. So before we just answer that, what you got to think of is that there's a regression line for the entire population. All right, that there's one true regression line for the entire population. So if we can take all the cities in the United States, put all their latitudes and average January temperatures into a model, okay, we would get one population regression line. All right, and so that would be the model. In your next regression course, we would add something to this, okay? But for right now, let's keep it simplified, okay? And notice here, instead of using B0 and B1, we're using beta sub 0 and beta 1 here, okay, in the model. So beta sub 0 is the population y-intercept. Beta 1 is the population slope. So this first line is testing if the population y-intercept is equal to 0 versus not equal to 0. Here's the honest to goodness truth here, is that this is rather an unimportant test, okay? There are special situations that you would go over in regression course where this test might be important, okay? But you got to have a real specific reason to probably take a close look at this, okay? And so really what we should focus our attention on is the second line here. That and by the way, if you looked at another computer output, they might not call this intercept and slope, but I don't care, all right, because I can guarantee you that no matter what they call this right here, okay, and no matter what they call this right here, all right, that the first line is always testing the population y-intercept, and this bottom one is always testing the population slope. All right. So let's concentrate on the bottom line. This test is testing if beta sub 1, okay, is equal to 0 versus not equal to 0. And this is called the slope test. Now this is an important test. Okay, this is truly telling us something. So the first thing I want you to notice is that the alternative has a not equal to sign. So it doesn't matter if the relationship is negative or positive. All right, it will account for such things. Um, so that would be the default in any computer program. You could test either one with this hypothesis test then, all right? So it doesn't matter if it's negative or positive, and you'll just probably just leave the default as not equal to 0. Why are we testing this? Well, if beta 1 is equal to 0, that's basically saying that there's no significant relationship between what? Between x and y. Because if you're, remember what we talked about back in Intro 1, get my cursor here. If we had a relationship where we had the big ball of nothing, right? We started seeing stuff like this, okay? Very little to no relationship. What's going to happen to the regression line? It's going to go straight across like that. And so what we found out is that when the slope is 0, there's no relationship between x and y. So that's what's in the null. In the alternative, notice what's in there. Beta sub 0 is not equal to 0. So what that's saying is that there is a significant linear relationship between x and y. So this line is testing basically this. All right, so you could replace this with that if you wish. Okay, you're thinking anyways. All right. Now, what's the test statistic? It's in terms of t, and so here the statistic that we would throw in there is b1. Okay, that's a sample slope, and it would be minus 0 because that's what's the value in the null, and then we would divide by a standard error of b1. Okay. Now, here's the thing: is that the standard error formula is a bit long and ugly. Not as ugly as those degrees of freedom for the two sample t-test, but it's pretty long. Okay, and if you wanted to check it out, you can go to page 573 in the book. But more important, what exactly is this? Well, let's think about this again. So remember when I had originally Lincoln, then I replaced it with LA, and then I got two different sample slopes. Okay, and so we just learned that the sample regression line will produce different y-intercepts and slopes, okay, depending on which cities that you brought into the sample, right? So the sample regression line varies from sample to sample, all right? That means the y-intercept and slope varies from sample to sample. So what this is the estimate of the standard deviation of all possible sample regression slopes, okay? So that's what this guy is down here. All right, so if you went ahead and figured this out, if you take this number right here, okay, which is B1, that's the sample slope, all right, and minus 0, right, because that's the value of the null, and divide by the standard error, you would get that value right there, okay? So that is the test statistic. This is the test statistic, and it's in terms of t, okay? So that's the test stat. Notice the p-value, it's really, really small right here, extremely small, less than 0.0001. And normally with all regression analysis, you usually set alpha to 0.05. And so we're going to go ahead and reject the null. So we think that beta sub 1 is not equal to 0. And what does that mean? We have sufficient evidence at the 5% significance level. There exists a significant linear relationship between latitude and average generating temperature for all the cities, not just the 10 cities. Okay, we see that relationship, but can we take that relationship that we see in the sample and apply it to the entire population? We can. All right. So the slope test, pretty important test here. Okay, that's telling us that that probably we should keep latitude in the model to help us understand average generating temperature. All right, how about this bottom table? We're going to see this table again when we do ANOVA, analysis of variance. And so I'll just explain a little bit about the table now. So when we get to ANOVA, it'll sound very familiar to us. So the first thing is that we're running the F-test And so notice here we have SS and MS. SS stands for sum of squares. And so we're summing the squares of something. Okay, so we're squaring a bunch of things, and then we're adding them together. Okay, and then MS stands for mean square. All right, the F stat up here, all right, what that is a test statistic, and it's in terms of the F probability distribution. So we have another probability distribution. So let's see, we had the binomial, we had the standard normal, we have the T, now we have the F distribution. The only thing I'll tell you about the F distribution is that it's kind of funky because it has actually a numerator degrees of freedom and a denominator degrees of freedom, and that's about as far as I'm going to take the F distribution. Okay, when you get into a higher stats course, if you're majoring in stats and you take theoretical statistics, you'll check it out a lot closer then. Okay, that's where I'll stop there for talking about the F distribution. So the way this table works is that as you move down the table, things sum up. All right. As you move left to right, things divide. Okay, things will divide at that point. So down adds to when you move to the right, they tend to divide. Okay. All right. So this guy here would be the degrees of freedom for what we call regression, and this is the degrees of freedom for error. And if you add these two up, you get degrees of freedom in total. All right. If you take a look at this one, the sum of squares of regression plus the sum of squares for error will equal the sum of squares of total. All right. The reason why we don't add these two up, because that wouldn't make any sense, because actually we're dividing stuff. They have different denominators, and adding them up just really wouldn't make a whole lot of sense. Okay, it doesn't tell us anything. Okay, but these adding these two up do. All right. So notice here that if you, I know it looks a little backwards, and I don't know if I would have set it up like this if I created the first ANOVA table. All right, but if you this number right here, okay, the MS for regression is the sum of squares divided by its degrees of freedom. The this number right here, the mean square for error, what that is the sum of squares for error divided by its degrees of freedom. Okay. So, and finally, maybe the most important thing is that the F stat. What is that? It's this number here, MS for regression, divided by MS for error. All right. So that's how the numbers come about, and then obviously we have a p-value here. All right. So what exactly are we testing with this global F test? If we just have one explanatory variable in the model, the F test will tell us nothing new versus the slope test. Actually, if you just have one explanatory variable in the model, the p-values for the slope test and this will be exactly the same. All right, and actually, if you took the test statistic in the slope test and squared it, you would get exactly this right here. Okay, and I'm not going to go back. Just maybe trust me on that one. Okay. However, this test does indicate something if we are testing more than one explanatory variable. So now we're getting into what's called multiple regression. So let's say if we had 4 explanatory variables in the model, okay? And so we actually have 4 different slopes here, okay? 4 explanatory variables, okay? And so what this F test would be telling us then is that you would be testing this. All beta sub i's would be equal to 0, and the alternative is at least 1 beta sub I is not equal to 0, at least 1, okay? At least 1. So let's do this. Let's add longitude to the model and see if it improves it, okay? And the F-test will be the first indication if things are improving. So I did that. So up here, don't get lost in all my stuff on the page here. What I've done is that I've added longitude into the model, okay? These are the different slopes that came from it, okay? All right, so let's go to the F-test. The F-test is telling us that, oh, okay, it's less than 0.05. That's telling us that at least one beta sub I is what? Is not equal to 0, okay? So then we go up to, so then we have to say to ourselves, okay, well, which ones? So let's take a look up here. And notice here that when we added longitude into the model, it didn't really mess with latitude at all. And when we analyze longitude basically by itself, all right, notice it is significant. It's less than 0.05, the t-test. And so, so what this is telling me is that not alone does latitude, not alone was latitude a very good starting point, adding longitude in there seems to have improved the model. Okay, what model? In basically predicting average January temperatures for U.S. cities. Here are the different statistics that come from there. So root MSE, that's just the square root of MSE, meaning remember the value for S, okay? This is just a fancy way of saying S, okay? And then we got R squared, okay? Then we got R, let's not worry about R squared adjusted right now, okay? Let's not worry about that. But that's part of the output, okay? So, like I said, at least one population slope is not equal to 0, okay? And let's take a look at what happened to the model. So this was the model with just latitude by itself, okay? So this is just latitude by itself, all right? And this is with, over here, with latitude and longitude. What happened to S? S went down. And do we want S to go up or go down? We want it to go down. That's what happened here. That's a good thing, all right? And then R squared went from 0.9654 up to 0.981, okay? So by seeing that both of our t-tests here are significant, what that's telling me is that the model improved, okay? S went down, R squared went up significantly. Remember, R squared can only get up to 1 or 100%. And so going from 0.9654 up to 0.981 is actually a significant jump in this situation, okay? And so that's what everything is telling me there. Well, let's do this. Let's add average January snowfall to the model now. So now we have latitude, we have longitude, and we have now average January snowfall, okay? Let's see if that adds anything to predicting average January temperature, okay? Let's take a look. And so here's the F-test, and okay, it's rather significant. And so that's telling us at least one beta sub I is not equal to 0. It's not telling us that all of them are. They could all be, but it just is telling us at least one is, okay? So let's take a look. So looks like when we put in average January snowfall, it didn't mess with anything with regards to latitude and longitude, okay? However, let's take a look at the t-test, the p-value for the t-test with regards to average January snowfall. Oh, is that significant? No, it's not. So based on the p-value for average January snowfall, this variable is not adding any value to the model that already includes the other two. So let's take a look here. Here is the model with latitude and longitude, all right? S turned out to be 2.54 essentially. And what happened to S? It went what? It went up, didn't it? We don't want it to go up. We want that to be as small as possible, okay? So, that's telling us that, okay, maybe we shouldn't have put average January snowfall into the model, okay? Um, the last thing that we should take a look at here is R squared. Now look what happened to R squared. It went from 0.981 up to 0.9832. It actually did go up, okay? And there's a reason for it, all right? So bear with me, all right? But I think everybody would probably agree with me that knows some statistics that we probably should not be putting average January snowfall into the model, and that we should either stick with just these two variables, or if we really was not satisfied with our model yet, add a different variable other than average January snowfall. Average January snowfall, based upon the t-test, is not adding any worth to the model. But we have to figure out, why did R squared still go up? So a warning about R squared. No matter what variable you add to the model, R squared mathematically will always increase. It has to. Mathematically, it always has to increase. All right. That's why looking at R squared by itself is insufficient. You must look at other indicators as to whether the model has improved. That's why we were looking at root MSE. Okay. You got to look at the t-test. You got to look at the slope test. All right. And then make a decision. Okay. So now there are other things to look at, such as R squared adjusted, a confidence interval for the population slope, verifying conditions for regression. I mean, there's a whole bunch of things that we could have looked at, okay? And including that, if the conditions don't hold, how to modify, right? How to modify it. And so there's a whole bunch of things that we could have looked at here in chapter 10, but he had to kind of keep it under control, okay? We also didn't talk about if the relationship is nonlinear, right? Believe it or not, you can actually add explanatory variables to the model that are categorical. You would add what's called a dummy variable to this, okay? So there's many other topics, okay, that you can talk about with regards to regression. I mean, a lot, okay? All meant for another regression course, or for that matter, courses. If you were getting an undergraduate degree in stats, you would take a whole semester of regression. If you're getting a master's degree in stats, you would take another stats regression course. And then if you're getting a PhD, you would take another course in regression. And then if you're majoring in regression analysis with your PhD, well, guess what? There's more to learn. Okay, so there's a bunch of topics here. Okay, that is meant for another course. All right, that takes us to the end of the inferential part with regards to regression. Thank you for your time.